So I think I talked to most of you about this already in the last days, but I was trying to use a long short-term memory network and later SHAP to determine the impact of drought or like water surplus and the season on winter wheat. And goodness, Okay, and the idea behind this is that extreme weather events are going to increase with climate change. That means like extreme weather events like a drought or heat waves, for example, they're going to be much more common in the future. These events have large impacts on crops. As you can see in the background, this is a picture from Germany in 2018, and this was a potato field before, and looks like more like a desert now. And to estimate this impact and later probably attribute it to the weather events, this is a really difficult issue. So here I have the impacts on winter wheat. So as you can see, like the winter wheat is planted somewhere here. So that's basically you cannot see the month down here, but this basically starts in September, October. So you plant the seed into the soil, and then the winter wheat keeps growing until it's over there in July, August, when it's ready for harvest. So this would be the phenological cycle in Germany. It may vary in different countries. I think here it's much faster probably. And what you can see here, because the image quality is a bit bad, I just didn't have a better one, is that usually there will be snow covered here, or at least partly. Now we have different impacts, different extreme weather events. For example, excessive dryness, that would be a drought, of course. Excessive wetness would be like there's too much rain. And then we have heat stress and cold stress. But today, since I only have the data of the SPEI index, I will only focus on excessive dryness, drought, and excessive wetness. It means water surplus. So water surplus, for example, usually increases the risk of diseases. I put a circle here, but actually every time the wheat plant gets too wet, the chance is much higher for fungi or something. It's the same. Like I also put it on the final plant in the last image. And what it also causes is lodging. Lodging is something that the plant falls over because the roots cannot grab to the moist soil anymore. So there's the soil is really wet, and the roots kind of cannot take the weight of the plant anymore, especially if there's some wind or something like that. So these are the problems with excessive wetness. And obviously, if there's a drought, excessive dryness, there's things like you have a limited root development, for example. So the roots don't go very deep into the soil because the soil is really hard. Also, the plant height is usually limited. What happens is that if there's limited water, the plant still tries to produce some seeds, and that means it just doesn't grow that high and produces a few seeds there. So also the seed setting is reduced, basically. So this would be the problem with the excessive dryness and excessive wetness. But of course, we have other things that we will later see in the data. For example, if there's a drought in May or so, most likely this drought is also accompanied by a heat wave because it's really hot. It's usually if it doesn't rain, that means there's no cloud. That means that the sunshine is usually just coming through. So everything today is a bit limited. Everything I'm presenting today, because I'm just focusing on the SPEI index, but there should actually also be a heat wave index along with it, or like a cold stress index. Okay, so the data that I had available for this analysis is the SPEI index that you can see here. It's standardized. That means if it's negative, like it goes around 0, following this normal distribution curve, more or less. So if it's negative, that means we have a drought stress, and if it is positive, that means we have a water surplus. And here in the middle is just nothing, basically. So this would be like either drought stress nor a water surplus stress. And on the other side, I have like the same, like also index for the yield. And this uses like 30 years of yield data in a 10 by 10 kilometer grid for Germany. And if it's blue, that means there was a surplus in that year. And if it's red, that means there was a yield loss. And the nice thing is both of them are standardized. That means we don't really have to do much before inputting this to a machine learning system. So, or to get it to the same unit or something like that. So my first step, I will show you later in the notebook, is like loading these two netcdf files and then trying to extract the following. So I have the harvest date, basically. That's usually a month, let's say August or July in Germany. And from that month, we have the harvest index, because at the moment when the farmers harvest their field, they more or less know how much they harvested. And based on that, I can say if it's a good or bad year. That's the first part. And from that, we're going back, like this is the harvest month itself, and this is 1 month before the harvest month, 2 months, 3 months, 4 months, and so on, until 2 years, like 24 months before the actual harvest date. And so this is basically the data we're working with. We have this is basically our target. This is the harvest index. Was it a good, was it a bad year? And we try to predict it from the drought stress. Yeah.
So I'm assuming that the index, which like the harvest index here, is normalized between a range between 0 and 1, right? Or something like that?
It's between minus 3.08 and plus 3.08, same as the SPEI. I could have also like normalized it to 0 to 1 or something like that. Okay. Probably it's better, right? To normalize it to 0 to 1. Yeah. Okay.
How is the distribution of the output? Like the harvest?
You mean
does it follow a normal distribution or
yeah, it's
or is it like super skewed one of the sides?
No. It's actually both. It's a normal distribution, but it also depends on the amount of data we have. And since we have a lot, that means they're kind of normal distributed.
Okay.
Yeah. So I trained this network using I actually split the training and the test data set to 2/3 and 1/3. The 2/3 for the training and 1/3 for the predictions, and I had like 90,000, bit more, 90,000 of these yield measurements plus the 24 SPI measurements for the training and 45,000 to test it. And this is basically the result. I think the regression line is not exactly where it should be for some reason. It's a bit different than what's actually slope and intercept there. I don't know, but yeah, probably there's some matplotlib thing that I didn't see or whatever. And but actually predicts quite well. So overall, you can really like somehow predict the yield anomaly from the drought. And if we take that apart, then we can see this. So the most impactful month were the 6 months, like month 1, 2, 3, 4, 5, 6 up here. Before the harvest. So that's really funny, because it's usually in line with what our co-workers and our collaborators at JRC always say. They always say like drought is only important 6 months before harvest, and this is basically kind of proving them completely right. The most influential month is actually the harvest month itself, which is sad for me because I kind of wanted to show like you see, like it's really important that in May there's enough water for the plant to grow. It's not like the harvest month means that if the soil is really wet, for example, then you cannot go with your tractor into the field to harvest everything. Or if you still can go, then probably also your harvest is wet and you have to throw it away, or I don't know. It's probably full of fungi. If it's really dry, it's usually really good because the plant, as you can see in yellow over there, is anyways dead, so it doesn't matter how much water it actually gets. And if it's dry, you can just really access the field with your tractor, and the quality of the grains is really good because it's dry. The first phenological, the most important phenological variable here was the seed setting. So this is basically when the flower of the winter wheat kind of converts into the seeds. And so if there's a lot of water available, because this is a kind of the plant kind of needs lots of resources for that, then probably there's just more seeds produced per plant, and that makes it kind of more efficient. This would be my interpretation. And if there's too little water or too much drought stress, then not so many seeds are going to be produced. The next, I would say, 4 of this group is of course like the early root development. For example, if it's really dry or if it's really wet, then the roots don't really develop. That could be a good indicator. Then 4, actually I even Googled that. So the flowering of the winter wheat doesn't really have to do anything with the water. Like if the plant is water stressed at that moment, it doesn't mean that it's actually going to not going to flower or anything. Probably this is rather correlated with the heat stress at that moment, because most varieties of winter wheat that we use in Germany are not really up for heat stress. So if in end of May, more or less, when winter wheat flowers with us, and you have a temperature over 30, 32 degrees, then the plants all become sterile. That means you don't harvest anything. I think here it's probably different. I mean, yeah. And so one thing that was also important was the final growth of the seeds. So they might already be there, the seeds, but then they don't grow to their full weight or something like that. And the stem development was also kind of important. and the others I don't know. Like this is the most important factor in winter actually. That could like my interpretation would be that probably has to do with snow cover or no snow cover or something like that. Technically, the plants have to be covered in snow just to be a bit protected by for wind or whatever. Could be an interpretation. And then there's of course things that I really don't know what to say about it. So like the 2 years before harvest, that they kind of still seem to be in there, but it just might be like an indicator of the region. So like in this region, usually you have like this and that variation or so. So I don't know. It's also like less than, I don't know, 0.7 or something. So it's probably not so important. Yeah.
What is the life cycle of
The winter wheat?
Yeah.
Yeah.
From September to August?
Usually like from October to July, August, yeah, depending a bit on the weather.
So less than 12 months.
Yeah, yeah. You usually harvest in August, and then you have like you wouldn't sow the like you wouldn't put the same crop usually on the same field again. So there'd be something else then. Like you would put whatever you have, potatoes, rapeseed, something like that. No, potatoes not in winter, but rape, like you know, like something like oil fruit or so. It's just to change it, not to have every year winter wheat. But technically, you could then like if you harvest your winter wheat in August, you could have something like I don't know, something like small thing that just grows to that size, and then you would put it in the soil again, and you would probably just put winter wheat again in October or so, like 2 months later.
Because if you start in August,
Yeah.
How is this trying to understand?
I mean, you cannot put.
Before. I mean, like the plant was not even there.
No. It's 2 years before harvest. I think it's just because like probably a thing about the region, for example, that in this region there's a typical thing, you know, like the harvest, like if it's prone to be like droughts in August or so, or it's like I don't know. Actually, I have no idea.
Wouldn't it be better to just take 10 months after growth?
Yeah, I actually thought about it, but also yeah, probably next time I'm running it just for 1 year or so. But it's still interesting to see it like that too. That it kind of seems to be relevant to what happened 2 years before. I don't know. Yeah.
Actually, that might be evidence that some of these features they already don't mean much.
Yeah.
So, for example, one of the things that people are doing in random forest is to add one more feature that's just like noise.
Yeah.
Right? Just a random feature. And then if the other features of the data, they kind of they have the same importance of a random variable, then you say that those features that have even less importance than a random feature, they are meaningless, right?
Okay.
So one thing that you can do is try to apply some sort of thresholding for the features that you have, right?
Yeah.
So for example, we don't have the strategy of like adding a random feature like they do in random forest, because the whole rationale behind SHAP is like game theory, which is a little different from random forest. But one thing that you can do is to remove data from your table and redo the training, you know?
Yeah, of course.
Just as you were saying, like train with just 1 year, you know?
Yeah.
And see if that impacts anything on your performance. So most likely you're gonna show that like data that goes beyond 9 months doesn't mean anything. So like it's not gonna affect anything in your performance.
Yeah.
Right? So yeah, that's something that.
Yeah, something that I want to point could be that previous year can have an influence in the cycle of the weather pattern. So usually we have a 10 years cycle along the earth according to La Nina, El Niño, and so on. So it could be that the previous year is telling us in which cycle we are, in which moment of the 10-year cycle is doing. So could be that is still bringing some information, okay, for the 24. So and the LSTM, you've been training. Okay, this is just variable importance.
Yeah, exactly.
So LSTM coming now. No?
No, I will show it in the Jupyter notebook.
Okay.
Yeah. So yeah, basically the idea, like what I would now try to do is like exactly like try to implement your ideas. Like first of all, like just scaling it between 0 and 1, then just having probably a random variable in it, or like just like shortening it to 12 months or 9 months only. And then later I have more stuff actually. It just didn't manage to get the data ready last Saturday. So I also have a heat stress index, for example. I might probably also look into like a cold cold stress or frost index or something like that. And I also wanted to add like soil moisture, and then maybe I can add lots of things like like for example the NDVI for every month or something like that for the area. That would be interesting, like just adding a remote sensing vegetation index or something like that. I think that that might also be very interesting. Yeah. Okay. I don't know. It's done. It's done. It's like the whole part of the presentation that should have moved. Okay.
Okay.
Okay, so this is the Jupyter notebook. I'm using a few more libraries that I import lower. I think it's a good practice to import everything up here. But yeah, so first of all, I load the data as X-array. Like it's a X-array is basically a data format. I think it's also built on NumPy. So it's like I use 3-dimensional ones. That means you have like a longitude, latitude, as well as 2 dimensions. And like, as you can see here, latitude, longitude, and then you have a time dimension that goes basically in the back. And for this data or this data here, I have like monthly data, and for the harvest, of course, it's yearly data because we assume only to harvest per year. Yeah. Another thing is how I got the how I managed to get the we can even go deeper, like this is the index. So how I managed to get the harvest dates is this, like in Germany was kind of categorized in the 50s into natural areas. These are areas that have a similar soil type and a similar climate and a similar, like they're kind of similar for ecosystems. And we have 92 of these natural areas. I just made a raster out of it. And so like the value, as you can see in this raster, goes up from 0 to 92, I think. And with this, I more or less know that all the all the crops in this area were more or less harvested at the same time. This is the idea behind it. And then I took another data set because with every bigger weather station in Germany, also usually the harvest or like sowing dates or like the different physiological phases of the plants are recorded. And then I kind of like used that other data set to get the mean or the mean values always for these areas. So I know more or less that in this area, the harvest date would be like August or something like that. Yeah. Okay. So the next thing I had to do that was then, clean the data a little bit around the coordinates. For some reason, like the coordinates are always like randomly long whenever I import them. And yeah, so we can even go down. I think it's just cleaning the data exactly. And okay. So what I did in the cell before, like one up, is basically here is I concatenated all these data sets to one big block basically, and then fed them into this apply function. What it does is if you imagine your data cube like that, that it just takes every pixel from the time through the time dimension. So basically, if you have a data cube with a with different maps stacked above each other, then you can just say for this latitude and this longitude, this is the time series. Yeah, and because I stacked them on top of each other, I had to take them apart inside of that thing again. And basically, this huge code block, what it does is creating me a Jupyter notebook that has the index, the yield index first, and then it has the 24. This is in the back. It's kind of a long code, and I could have put a bit more effort writing that. So this is exactly what the data looks in the end. So we have the year, the harvest year, the harvest month, -3 always or -2 always here, and we have the natural area code, and then the yield, like the actual yield, the yield anomaly index, and then all these SPI drought indices basically. Okay, so with this, I think
what's the difference between the yield and the index in this case, or the
no, yield is in decitons per hectare. So that means in this area, 7.2 tons per hectare of winter wheat grains were harvested. And this is like just the absolute thing, but you need a relative. Like you have to know if it was a good year or not a bad year for exactly that grid cell, basically. Yeah. And the index just tells you that this is positive. That means it's slightly better than what you would expect.
Okay.
Yeah.
The maximum 3.8 is that. The maximum being 3.8.
The theoretical maximum. Yeah, exactly. Okay. Yeah. Okay, yeah, exactly. I think it's basically the data frame. I saved it, and then that's where we start with the machine learning part below it. Yeah, so I've actually pretty much used your script, like a combination of your script and something that I found on the internet. So this is actually based on Keras and TensorFlow, not on PyTorch. And I can just go down. Yeah, maybe I should suppress these warning messages. So the idea is this: like I had to create a data array that would follow more like this structure that had basically the time series for predictors, and then in the end that would have for y only the target variables basically. So I did it here. I just took apart the pandas data frame basically, made a list out of it, split it into train and test data. As I said already, like taking like 2/3 for the training and 1/3 for the testing. Then I defined the model here. Yeah, I think I just really took the standard model. I can probably play around with this quite a lot. I don't know. And in the internet, it said I found in several places that this vanilla version that everybody has works quite good already. But of course, like I can probably just think about how to improve it. If you have any improvements, what I could do here, please tell me. Yeah, and
So you didn't normalize your data?
Hmm?
You didn't normalize your data?
Not yet. No. I thought it's standardized, so that would probably be enough. But
yeah. Okay. Yeah. It's the red case that.
Yeah.
Okay. Yeah.
But you're right. Definitely, I will try to normalize it, like to make it 0 to 1 or something. Yeah.
Yeah. That's usually helpful, but indeed, like our data seems to be like normalized already, right? Like,
Yeah.
the way coming from.
Yeah.
Okay, yeah.
Okay, so I had to reshape it into this shape that is sample, like from samples time steps only to samples time steps and features. This is the thing that you would usually do. Then this is out-commented now because I don't like to run it so often. Like here, the model is fitted basically. I think running the model on my computer took like 4 hours or so with all these things. So yeah, then the model is saved here. I just load it again. So like to skip this part basically. And then I do a bit of reformatting to like just have a nice plot down here.
Okay, can you maximize the part?
Yeah.
Like zooming? Yeah, thank you.
Yeah. Okay, so and this is what I got like from the 45,000 predictions. Actually, we have a slope of almost 1 and an intercept of a bit more than 0. And that resulted into an R squared of 0.84, which is kind of good, I think. Yeah. So I mean, it had to work in a way, right? Even though it was not normalized. So yeah.
That's good.
Yeah.
Okay, so due to that, you have a very high accuracy. This kind of prediction, okay, how you can use it in terms of forecasting to see the yield production, because we see that the most important month is the last one.
Yeah.
So the last one, you means that you are already invested.
Yeah,
so
yeah.
you,
But it
over
doesn't.
here 1 month before, probably you cannot really say.
I mean, you can, but if you have the data of the last month, you're already like 2 months ahead of the market, I would say, because the farmers have to get the grains to their silos, and this is like kind of marketed and so on. And I think the harvest is only on the market in November, maybe. So it will take a bit of time to transport it around. It's not really like for prediction. You're right. It's a bit late, maybe.
Because over here, I mean, if you stop, actually the second month is here.
Yeah.
So there's 2 months before, it doesn't tell you so much.
Yeah,
The one that's really making the difference is the last
month. Yeah.
Is the last month.
Yeah.
So we cannot really help it.
That's pretty good, man. Look at 3 months before you already have like pretty high importance for that month.
I mean, you can make a guess, I think.
Yeah, you can make
3 months, you
yeah.
can save your crop, maybe.
And it's still only one variable, actually. You only have like drought, drought or water surplus. What's actually really missing is, I think, some NDVI.
Yeah. Okay.
That would be interesting, and of course the heat stress, because heat stress will have most impact in May. That's the year 4 months before. So
Okay.
yeah.
Okay, very good. Any other question? Okay, perfect.
Thanks
Thank
a lot.
you,
then.
Florian.